Welcome back to Cradle to Grave Algebra 1. My name is Mark Gingras. Today we're going to talk about sets. And you might say, well, what's a set? Well, a set is nothing more than a collection of objects. And I'll show you a couple examples how to denote those with mathematical expressions and some properties of them. So first thing you want to do is understand what this curly brace means. And all it does is it contains the set. So we have an open and a closed curly brace, and whatever's inside is inside the set. You can have a set of numbers, 2, 5, 8, and 9. You can have a set of letters. You can have a set of anything you want. In fact, you can even have a set of narratives, all odd numbers. You can have sets that are empty, and I'll show you what an empty set is in just a moment. But a 0 is not an empty set. This particular one, this 0, is a set that contains just one element. So element is what's inside the set, each element. And in order to make that a null, which means an empty set, truly nothing in there, and basically you would put a line across it like that. So I don't know how to do it with the keyboard, but that's called the null set. When the line is going across like that, that means that it's not a 0. It truly is an empty set. Also, so another example would be you have the curly brace and you actually literally have nothing in it, but that doesn't look good. So we usually put the null in there saying this contains nothing, literally nothing. So imagine nothing in there. So this is just a way to denote that. So you see all these different methods for actually denoting what's inside of a set. And again, each object in the set is called an element or a member of that set. Let's have one set, and we'll call it A. We'll make it a bold A, actually. So, okay, so it was bold. So actually, we'll just make it a regular A. A is equal to, and we'll say the set 1, 4, 8, right? Now let's create another one called B, and we'll set that one equal to 4, 1, and 8. All right, so what we can say is we can actually say that A is equal to B because there's a one-to-one correspondence from all the elements in A and the elements in B. In other words, for every element in A, it matches something in B. So, these 1 and 1 match, the 4 and 4 match, and the 8 and 8 match. Notice that the order does not matter. So if order doesn't matter, you can say rearrange these all you want, and A will still equal B, B will still equal A. Okay, so how do we denote what's an element of a set? We can start that by saying you can have an assertion that the number 1, let me back up just a tad and make this thicker. You say the number 1 is an element, so this little E symbol, element, it's like a squirrely little E. 1 is an element of the set A. Is that true? Yes, I'm telling you it is true. 1 is an element of A, because you can see A is here, and 1 is an element of A. Now let's just say 10 is not an element of A, so you would simply do the E, which stands for element, and put the line through it. And that just means 10 is not an element of the A set. You could have easily just said the same thing by saying 1 is an element of the set containing 1, 4, and 8. That's just as good. So either way works. It's just a little easier to use the A than representing the whole set every time. The set could have an infinite amount of numbers, like the set that I just talked about where it was all odd numbers. Odd numbers go on for infinity. You couldn't possibly write that out. Okay, so that's what element of or a member means. Let's move on. I will clear this, and let's talk about subsets. So a subset means that some of the elements are in another set, but not necessarily all. Let me give you a couple examples here. So let's just say A, or let's call it T. T is equal to the set of numbers 1, 2, 3, 4, 5. And we'll say U, let me move this over actually, Just a tad. There we go. We'll say U is equal to 2, 4, and 5. Well, we can ask questions about these sets and answer them. We can say 2 is an element of T. That's a true statement. We could say 6 is not an element of T. We can also say 6 is not an element of U. Now, we cannot say that T is equal to U, even though they have some correspondence. They have some things that are equal in here, like the 2 and the 2 match, the 4 and the 4 match, and the 5 and 5 match. But the 3 and the 1 are missing, right? So let me remove those. I forget how to do redo with a shortcut key. So T is equal to U. That is not a true statement, so you have to put the little thing in there, just like everything else, the little line. T does not equal U. That's a true statement. However, U is a subset of T. So the subset symbol is just this U looking thing that's sideways. So U is a subset of T. That is a true statement. So for every element in U, you will find that in T. You did find a 2, you did find a 4, and you did find a 5. Now if we had another one called W here that equals, let's just call it 2 and 7, you could not say W is a subset of T because this 7 doesn't belong in the T. I hope that makes sense. So that is not true, and so for this U, you would do, again, put that line there. W is not a subset of T. I can't pull out the 7 from T, so it's not a subset. It's just common sense almost. It's very intuitive on this one. Okay, finally for this example, let's do, well, let me clear this board a little bit. Let me just go ahead and delete this side here. I'm getting used to using all these technological devices here. My head's in the way, so I'll jump out of the way here. So we have W, you have U, you have T. You could say, again, we could say that U is a subset of T, but you cannot say that T is a subset of U because every element in T cannot be found in U. So it's the other way around, it makes sense. U is a subset of T, but T is not a subset of U. However, T is a subset. Oh, let's just make this clearer with the little nod in there. T is not a subset of U, but T is a subset of itself. T is a subset of itself because every element of T, 1, 2, 3, 4, 5, can be found in T. So it's a subset. It's a subset containing all of the elements of T, but it is a subset. So that would also mean U is a subset of U, and W is a subset of W. Clear as mud, right? So this is just set notation, and you're going to have to learn more about sets throughout this course because it's very important to know what a collection of objects could mean mathematically. Finally, we could say things like, we can be explicit and say, set B contains all odd numbers between 0 and 12. We could easily do that, right? So what would that set look like? So this is the narrative. Now what I can do is I can say, okay, let's try to draw that out. Let's try to draw that out. So we'll say B contains, so B is equal to some set. So set notation, the bracket, or the curly brace, I'm sorry. All odd numbers between 0 and 12. So 0 is an even number, so that's not it. 1, 3, 5, 7, 9, and 11, right? So B is equal to these numbers. So we can have a narrative. You can even say things like, let's try another one down here. We could say set F is equal to, and I'm going to put this in curly braces because this is also allowed. The narrative above me is just an actual sentence. Now this is mathematical notation with words inside of our set. So F is equal to all real numbers. Well, yeah, I'll just do it like that. All real numbers. And we could not possibly write this out. We cannot write that out because we can't write out all real numbers, but we can denote real numbers. Again, in the previous lesson, we could say f is equal to the set that contains all real. Remember that r, right? That little r, fancy r. I'm going to draw it out. Hopefully I can draw it out in that little spot here. So remember what real numbers are on that number line I was talking about. So it's like that double, it's like two little vertical things and then the r. So f is equal to all real numbers. 2.2579, square root of 2, 5/5, pi. All of those numbers are in this set. So virtually every number that you could probably think of is in this set. Now, you guys probably have not learned this, but you might have heard of imaginary numbers, which is they're not real numbers. But that's a few courses ahead of algebra. Probably get into that in maybe college algebra. Yes. Algebra 2, you'll learn imaginary numbers. So imagine that. You get to actually learn this awesome thing called imaginary numbers if you just get through this course. That being said, if this course was helpful, please put some comments down there, and I will see you in the next lesson.